So the title is Design by Simulation, a Workflow Demonstration. A preface before, as also already the colleagues of EDAC mentioned, the large amount of the presented workflow is based on results of the research project OptiMX. This is a project funded by the German Federal Ministry of Education and Research. We must state that the transfer of research project results into applicable and reliable software is a topic on its own. It's a lot of work, and this is still an ongoing process, even continued after the delivery of PERMAS and Whisper version 18 end of June. So this I wanted to say that this work is based on the funded research project, because this is a very important basis for us to do this kind of work. A short overview. As you see on the right, what I will present you is inspired by the rear wing system you've previously seen from EDAC. This is a little different kind of model, some changes later I will show you, and I also have to say that this work is done at a later stage of development, so this is something maybe this could not be done by EDAC itself, because this is very, very new developments I will show you here. So what I will show you is first I will introduce you to the FE model. This means I will show you boundary conditions and load cases. And the next step is a very important topology optimization step. So this first means the setup of the optimization task. Then next is the post-processing of results, and very important, the transformation of the topology optimization results into a new FE model. And then the last step is what we always recommend is to finalize this topology optimization by a shape optimization step. There again you have a setup of an optimization task and possibilities for post-processing of results, and finally the final design to be exported as an STL file. So this is the workflow I will present you, and now I will leave this presentation and switch to the PERMAS control center. So most PERMAS users know this. This is where you start all applications like Whisper and PERMAS. Okay, this is what I start with. I start with a Whisper session and load into Whisper the design space for the topology optimization and some additional data. As you can see here, this is the selected files. And this contains the initial finite element model. As before, Mr. Schilder told you from the process, typically you have a preprocessor of your choice where you can set up the FE model, and this is the starting process. When you've done this, this is the starting project starting point for the workflow I will present you. Here you see the design model for this demonstration. This is similar to what you've seen before. Difference is that we already modeled here the hydraulic cylinder to move the rear wing. Here you have the connection to the where the rear wing is fixed, and here you have some joints for connecting the rear wing system with a car body. I show you we have two load cases. This is the standard load case. This is just the force moving downwards, pointing downwards from the aerodynamic forces during high-speed driving. And the second load case is the brake situation, where you have additional component in horizontal direction, and together with pressure inside the cylinder, moving the piston outwards just to change the angle of the rear wing. This is what I show you here. So we have here some pressure forces here on the surfaces inside the cylinder. Okay, I remove this. Don't need any more. Now, the next is what I want to show you. This is the starting point from our process. So the next is what we simply do is to set up the first topology optimization. So in this topology optimization, we want to minimize the weight and want to fulfill some constraints on stiffness. Constraints on stiffness we have from reference solution, and have some values for the compliance of the structure for the two load cases we want to fulfill in this topology optimization. First, we create a situation where the topology optimization is performed, and then we choose the design space. In this case, this is very simple because we just simply choose every element to be in the design space. Because we want to do a minimization of weight, this is always an interesting question, how to start with which initial filling ratio you should start your optimization. In this case, we choose to start with a full model because we want to minimize the weight. So that's already everything you have to do at this stage. And then you say create design element. This means the basic definitions for topology optimization are already done. Now we go to the next page and have the possibility to formulate some additional conditions for the topology optimization. One important thing is that some parts of the structure should necessarily be maintained in the topology optimization. This is a so-called freeze condition we can choose here. And of course, we do not choose every element, but I have a predefined set called freeze. These are those areas of the structure that should necessarily be contained in the final structure. Of course, this is the cylinder. This is our here the fixations for at the car body, and also the connection to the rear wing here in this area. Okay, now I save this. And second is, always we do a topology optimization with a minimum member size filter, or let's say a design variable filter. This realizes the minimum member size of the structure. And we chosen here a minimum size of 8 millimeters. This is also because we want to ensure to be able to that the structures can contain the channels you saw in the previous presentation for the hydraulic fluid to supply the or to move the piston for the to move the angle of the rear wing. So we choose here 8 millimeter, and then we have a new feature in the developed in the OptiAmix research project, is that we additionally have explicit constraints on this sizes, which is that we explicitly want to constrain the minimum member size. This means the size of the structure and also the size of voids where no material will be contained in the results. So with these two conditions, we finish the conditions, and then we go to the constraints page, and this is where we define the optimization target and the design constraints. So as I said, we want to limit the compliance for the two load cases where we have values from reference configuration. So I give it a name. This is number 1. And create this design constraint, and I want this to be valid for the load case 1, and there I have a maximum an upper limit of 94.5. This is the value from the reference solution, and then I do the same again for the second load case with a different name. load pattern 2, and also maximum value. In this case, I have 117.5. Now, because we did not explicitly choose a design objective, Permos automatically selects the global weight as the optimization targets. This is exactly what we want to have. So at this point, we already finished our setup of the topology optimization. Now I go back to too fast. First is now a very important step. I have done the definitions for the topology optimization, and now I do something that is very, very convenient for doing different variants of topology optimization. I export just only the new items I just defined in this session. This is exactly the data for the topology optimization. And so I can export this data in a separate file. You see already I did this on Monday just to exercise this demonstration. So I do not replace, or maybe I can replace this is no problem. So I export this topology optimization setup in this file. And then now I can go to back to the Permos control center, and here I open a UCI file that controls the topology optimization. This is my typically work is that I always nearly use the same UCI file and just do some changes to read the correct files. Here it's already done. And then just this is for topology optimization, nearly all the same what's inside this file. Just a short explanation. I don't want to do a workshop here. But first is which input files should be read. Here with the topology optimization data I saved immediately. I saved before. And then I do a static analysis, a weight analysis, and then the topology optimization. And at the end of the task loop, which the optimization is done in the task loop, I define which results I want to export. These are very important, the XY plots of the history, except for example of objective function or of constraint functions. And when the final result is reached after the loop, I also export the displacement of the static analysis. So this job now could be run. I do not know. I did before because this job is something that takes some time. As I remember, this is something about maybe 2 hours. Then 2 hours later, you can have a look at the result. Of course, I did this calculation before, so the results are already available. So now I have to look that I find the right one from this run. Okay, this is this topo 1. So I will load this file, and this contains the final filling ratios of the topology optimization. This takes some time to be loaded. In the meantime, I go back to the Permos control center and open the Permos graph. This is a very easy tool to have a look at the already mentioned XY plots. This is a very important step if you do optimization, just to check if the optimization did what you expected when you formulated the optimization task. For example, you have a look at the objective function history, the weight, and you can have a look if it's really minimized. Okay, this looks very, very nice because this goes very, very down to nearly only 10% of the initial weight, so this looks good. Very important thing is that you have a look if all constraints are fulfilled. So you have a curve with a maximum constraint violation, and here you need to check this has no value higher than 0, because this would indicate an existing constraint violation. This is also very good in this case. Can also check specifically the compliance design constraints. Here you see I have previously given a simple, slightly different name, but the relative history, you can check if the design constraints reach the defined limit. 100% mid means they exactly reach the upper limit. This is the case for the two compliance design constraints. This looks very, very good. And also a very interesting curve is a curve about the non-discreteness of the topology optimization results. This curve indicates if you have only zeros and ones in the solution, or have a lot of elements with immediate filling ratios. If it's down to 0, then you have exactly only zeros and ones. So at the end we have a very, very small value, so this looks very good. Okay, now I'm happy with what I see, what I've seen in the XY plots. So now it is worth to have a look at the final filling ratios and to see what design proposal results from this kind of topology optimization. Therefore, I go into the visualization dialog. This is just one opportunity to have a look at the results. I can look at the Scala results of the elemental filling ratios. So with this view, you cannot see too much, but here in the table you have all the scalar values for the elements listed, and here you can apply, for example, you can apply a filter. For example, you filter out, or you extract all values that have a filling ratio higher than, no, stop. First, I want to show you something different. Before I told you about the non-discreteness function, here also you can see about how discrete the final result of the topology optimization is, because you can show a histogram of the table. Now I show a histogram of the complete table with filling ratios, and you see you have a lot of values with a zero filling ratio, and some values with a filling ratio of 1, and nearly nothing in between. This means you have a very, very good and discrete result of the topology optimization. Now I apply the filter I already mentioned. A filter that only want to remain the elements with filling ratios greater than 0.5, and then I can select all elements remaining in the table, and here you have a first impression of the design proposal from this topology optimization. And of course, now I can hide the rest of the, or I can show only this part of the structure. So this is the first result of a topology optimization. So already Mr. Schilder told you that we have some good opportunities to post-process and do a smooth model out of the topology optimization result. And this is something I want to show you now. So I close the visualization dialog. And now I go into what we call the design wizard. This is a very important part of the Optiamics research project, that we could be able to do or have to development the fundamentals that are implemented in the back end of this design wizard. Here again, you can choose the results of the topology optimization and the filling ratios, and then you create a volume. This volume takes a little time, because we also have implemented a so-called extension loop. This is that the selected volume is checked for irregularities, for example, T-edges or singular point connections that are very, very difficult for further processing. So if needed, the selection is extended by some more elements. Here you can see only very, very little, because the result is of the topology optimization very good. You see here the green elements where the algorithm finds they should be added to the selection to have a proper initial volume for the further processing. Now the next step is, if you have chosen this volume, is to create a surface mesh around this volume, a smooth surface mesh. Here you have several opportunities of parameters to control this surface mesh generation. Here you have an edge length factor. This means this defines how the edge length of the final surface mesh. I want to have exactly the same as in the initial topology optimization model, so I increase this to a factor of 1. And then I just try what happens. I want a very smooth result, so I increase this value, and then I try and want to see what's happening. So this takes some seconds. Time for me to take a little bit of water. So now you're here, you have the smooth result, but you also can see there are still some things you maybe are not very happy about. For example, here in this area, you have the boundary of the design space, and here you have sharp corners, and maybe you also want to smooth to get this also get smoothed by the process. This is possible because we have here the option to say, okay, also smooth the boundary. If we check this box, and now we do the same again, wait some seconds and see what happens. Just a moment. Okay, now this is much better, but also worse at some other places. For example, here now also these fixations are smooth and remeshed, and also here this cylinder. So this is undesired behavior. So to avoid this, we have also the option to define fixed nodes on the boundary. So therefore, I first need to define a node set. First we'll leave the design wizard and go to the selection and choose some nodes that I don't want to be included in this the smoothing and remeshing process of the design space boundary. So, for example, what's very obvious is that I choose the nodes where I have the loads applied and the SPCs. So this I want to select and exclude from the smoothing and remeshing process. And also, of course, here the inner of the cylinder, we should not change the shape, and maybe also here in the front, and also this plane here, because this ensures that I have a plane area where the rearing system is connected to the car body. Okay, now I can create a set and maybe name it this the fixed nodes set. Okay, I switch this off and then go back to the design wizard. The volume is still selected, so now we just set again the right parameters for the remeshing and smoothing, high smoothing level and smooth boundary, but with fixation of this fixed node set. Here you get shown again, and then I create again what we call a hull. It's actually it's a closed surface mesh of the by volume defined geometry. Again, some seconds, and now if we have a look at this, this looks much better. So I have a smoothing here where I want to have it, and I have maintained here the fixations at the car body, and they have maintained the exact shape of the cylinder, and also here of the connection to the rearing. Now I show you also now another impression of what you see here. So here you can also check how this surface mesh fits to the selected volume of the topology optimization results. And if you're satisfied, okay, you can create a new component. Component is something that is the basis for every FE model that you use in the PERMA simulation software. For example, I name this the hull version 1. And create a new component. So the next thing you can do, because remember the presentation of EDAC, this part should be printed. So in this case, we choose a little different printing direction. In this model, the cylinder here is exactly the 45 degrees. So maybe we think it's possible to choose exactly the negative Z direction as printing direction. So, and now we want to check if this is possible or where we need support structures. So we have here the opportunity to check the design and choose here overhang angle. We want to check if there's a violation of a critical overhang angle, and choose the build direction. Now we still move also the base plate to below of the structure, so that's all we need, and generate check data. Here we are. So, and now this is not very best scaling of colors or color table. So we have a predefined color table for overhang restraints, and we load this, and then we can see where the overhang, the critical overhang is violated. There's one big issue here, and then first I close, maybe, let me see this, I close again, we don't need, so you have a better view. So we have a violation here. Well, this is very pity, because this is a long way for support structures. This needs a lot of material for support. And of course also we have a problem here in this area, and this is maybe if, for example, here in this area, maybe this can be simply done by a shape optimization to change this angle here. But here, if you want to avoid the need of support structures in this area, you see here indicated in red, you need a different topology, because you need that the hole here should be closed. So with this in mind, we go back to the previous model. Now we have two components in this model. So we have an overview here. So we go back to the initial design space, and then we define a variant of this topology optimization. We go again into the topology optimization wizard and go to the conditions page. And now we add an additional condition for the topology optimization named design element for print 3D. And now here we can define first the build direction. So this we've chosen the negative Z direction. Define a critical overhang angle and some tolerance for support structures we would like to allow in the final structure, because sometimes it's not very useful to try to avoid every support structure, because this may also lead to some more kind of casting parts that we don't want to have. So we allow a little amount of support structure here. It's 5% of this relates approximately relates to the volume of the final structure. This is a small value, still allowing some support structures in some important areas. We save this condition, and then we can already close again this wizard for the definition of the topology optimization. And now that's the same game as before. I again save the new items, and now these are it's just a variant for the topology optimization. I can save in a second file. And now if I did so, I go back to my Permas control center. Now I open the UCI. And this is always what I do, what I recommend you. No, this was wrong. Yes. No, I don't want this. I want here. So this is my UCI file, and what I just have to do is just to change the input file of the topology optimization data here, and that's all. And maybe just for the export files, give different name or define a different directory where I want to store the exported files. So, of course, again, I did this already. So I already have results for this second variant of topology optimization. And I will find this here in this file. And I load this. And again, I go to the control center and open the Permas graph again to have a look at the XY plots. Now I load the XY plots of a previous run, and also the new one, just to have a comparison. For example, a comparison of the weight of the first run and of the second run. And what I can see, I need some more iterations, but at the end also I have a drastic weight reduction. And now if I compare these two solutions, I see that I have nearly the same weight. This is maybe just some several grams. What's the difference? So these all are a little below of 700 grams, just to give you an impression. And now, of course, I can also have a look at the non-discreteness of this new solution. Again, I have a very small value of non-discreteness, so I expect also a very good 0-1 distribution of the final elemental filling ratios. And I can also, again, check the compliance values. If they hit the 100%, this means that they reach the specified upper limit. Okay, in the meantime, I have the filling ratios loaded into the model. I have to state, maybe this is maybe something important. As you see here, I always use post file. This is because I'm a developer. I like ASCII files because I can have a look in. So it's I'm used to use always post files. Normally, for large files, the normal user should use HDF. This is much faster for loading, especially if you have big models. But I'm sorry, this is just my habit. Always, I want to have ASCII files to have a look in. This is why I always use post files. At the price that sometimes it takes a little longer to be loaded into Whisper. But I think for this is okay. And now I can also have a look at the in the visualization dialog, but I don't want to make it a bit shorter now. This is similar. Okay, I'll just have a look at the histogram. If we see again a clear 0-1 distribution of filling ratios. I think, and because Mr. Schilder before asked you what's a major difference of Permas topology optimization to other software products. I think we have a special emphasis on reaching clear structures in the topology optimization, and I think I would like to say that we are a little better in this issue than others do so. Okay, enough advertisement. Now I close the visualization dialog and go to the design wizard again. Okay, now this is the old HAL I don't want to see anymore. And then I choose the new filling ratios and create volume again. And also this algorithm again checks if there is some additional selection needed to avoid singularities and T-edges in the volume selection. So here we are. So okay, here you see we have indeed a different topology because the holes we had before here are now closed. And now I know I immediately go to the remeshing and smoothing. I use the same parameters. So here I also choose 1 at element edge length factor. Again, a high smoothing factor. I want to smooth boundary, and of course the set with the fixed nodes is still existent. Okay, then I start with the creation of the HAL or the surface geometry. After some seconds, so we have the new geometry, and this is something very, so as you see, this is very little manual editing. This is just setting some parameters, and then you have automatically a new surface mesh for a new model. Okay, now again I do a new component for this. Now this is HAL of variant 2, create a component, and then I can go to the design wizard again, do the same check for overhang angle, negative Z direction, move the base plate, and then generate the check data. already with the right scaling of colors. And here you can see this violation of the critical overhang angle is removed at this area. And here some violations still left, because you remember we accepted some tolerance of support structures, but much less than before, and especially these small holes where it's maybe a tedious act to remove the support structures from these small holes. They are closed in a physical useful manner. This is what the topology optimization actually does. So now we have a design that is, with regard to the need of support structure, maybe a more useful design. Okay, I close. I remove the result data. Okay, now we are very happy with this result of the topology optimization. Now what follows is that we want to do a final step of shape optimization. Maybe we are able to do some improvements on this design again. The first what we have to do is, for safely, what I do now is just first to export this model. So now I export this component. This is a simple surface mesh. I also could export this as STL file directly. Here I choose the PERMAS format, but this is whatever you want to do. This is not important. Okay, I export this hull of the variant 2, and then I go back to the design wizard. And what we want to do now is to create a volume mesh for the shape optimization. Shape optimization, what is very important is that we control local stresses in shape optimization. This is why I choose a higher order element type. I use 10-noded tetrahedral elements, and now I say create TET mesh. So this is an external TET measure where you can use every TET measure what is available, and that can be controlled by a simple by simple I think a Python script we use here. So now this is finished. Then I close the design wizard, and when I go here to the element heights, I see I have the plot now. I don't want to see nodes, I want to see elements. I have here the plot elements of the surface mesh and the new generated TET elements of the new volume mesh. Now I choose these plot elements because this is what I later don't want to have. So I remove them, go to the elements dialog, and delete them. So now this is a pure volume mesh, what we later want to use for the shape optimization. Again, I save this state. Component name is not very meaningful in this moment, but this is not important because later you will see what we do. Now I can choose to save this at TET10, for example, this file. Now I don't want to overwrite this because this is a file I previously saved, and I will use this previously generated volume mesh just to be sure that my results for shape optimization still match the model. So I hope you're okay when I start with the new session and I show you how to generate or how to complete this model with the loading conditions and the loads and the boundary conditions of the previous topology optimization. We do a different way. First, we start a new project and open the initial design space and the additional data with the loads and boundary conditions and so on, and load this original model again, where we started the complete process. And now what we want to do is just to simply exchange the design space by the newly generated design. Therefore, we have an so-called add and replace or assembly wizard. So this is the component we want to modify. And here we choose that we want to remove all existing elements and load a new component from a file. And this is exactly the file where the volume mesh of the generated design of the topology optimization is stored. I load this file, And here you can see how this will be placed in this original model. Okay, this looks good. Of course, they have the same coordinate system. And this is okay. Then I go to the next page. Then I see also the entities of the original model that need to be reconnected. But in this case, very, very simple, because we share, we have same geometry underlying, or same coordinate system underlying. Where I just press the button reconnect, and then I say finish. Okay, here I have an overview about the found entities that are now in the new model, and then I can have a look at the, for example, loading variant. And what I see, I have exactly the same loads as I had before in the initial model for the topology optimization, and of course also the SPCs here. Okay, everything there I need. Now I can start with a topology, with a shape optimization. What I should do initially is have a look at the stresses, just to know about the stress level. Let's remove this. Okay, and then what I have to do is to define an area where I want to optimize the shape. This is maybe the only time where the user has to take some care, that he carefully chooses a node set that defines the area where we want to change the shape, and for example, and also for where we want to control or examine the stresses. For example, I just use this here, and then I also can again deselect the areas where I have joints or where I have forces. No, that's wrong. Opposite, deselect. So, and also deselect again the region of the. So, first we need a bit. Okay. So, for example, this could be a set like this. Of course, I did this before this because this is maybe the only time where you have to take some care that you have everything inside your node set that you want to have. So I prepared this before, and I show you this definition. So we have this. Let me look on one upwards. Okay, we have here. Okay, we have here, this is the same model, but already done with a set here. Use a selection for the shape optimization, and also a set where I want to evaluate stresses. The second set also includes mid nodes. That's the difference, because I also want to have a look at the stresses at the mid nodes of the elements. So with these two sets prepared, I can go into the Freeform wizard and define a shape optimization. This is very similar to what you know from topology optimization. 3 pages, basics, conditions, and constraints. First, I need a situation. Then here, I choose the node set to define the area where I want to do shape optimization. Next is I define maximum shrinkage, or where how many material I can reduce. And in this case, I choose 5 millimeters and also growing 5 millimeters. And then what I do now is just create a design element. And now that's all you have to do. Again, you can have a look at the conditions page. Here in the initial run, we don't need any condition. We just need to define, again, the design constraints. I do the same as for the topology optimization. I have 2 design constraints for compliance with the same values. As I remember, it was 49.5. Save this, and also for the second load case, okay, a maximum 117.5. And now, very important. Okay, okay. What I need to do now is just with this model to run a simple static analysis. So first, I should go to where I am. Okay, here, and have a UCI-File, just using this model and do a simple static analysis, which normally you don't need. Export the stresses, and just to have a look at the stress levels. This is a very important issue. Now what you see here, we don't have a distinction between pre and post processing. So what I actually do, the definition of free shape optimization, this is pre-processing, but in the same session I can also do post-processing. This means in this case to have a look at the results of a static analysis. So I have nodal point stresses for the two load cases. Of course, here in this area, I have a stress peak. This is about 30 MPa. So this is a very, very low level. This is no problem. So in our optimization task, this is here in this case even lower. We don't need to reduce stresses, but what we want to do is that they don't increase. So I go back to the free shape wizard. Now I know I have a stress level of maximum of 30. So this is what I additionally define, nodal point stress constraint over both load cases. In this case, for von Mises stresses. Okay, all load cases, and I choose the set I've defined before to evaluate the stresses and define a maximum of 30. Okay, I save this constraint. Now again, as in the topology optimization, we try to find a lightweight structure, so we minimize weight again in this shape optimization task. Now I can save this again as new items. Let's name this maybe, for example, I have here a shape point dot. Okay, maybe we can do so. And of course, as you can imagine, I also did this run before. The UCI-File, maybe I can show you. This is very similar to cancel edit, open. So this is very similar to this for topology optimization, just different input files. And here on different commands, we do an optim, not a topo command. Then again, we have XY plots and the coordinate change. We export, this is very important. And of course, the stress distributions. This is also interesting. Okay, I did this run, of course, before. And now we want directly have a look what has happened. So I load this, should be this one, yes. So first, and also I can, of course, load the stress distribution of the final state. This is, I have this, okay, and I already loaded this, sorry. This was the stress distribution of the final state, and this is the coordinate change. So now it is clear. Okay, I can go into the visualization dialog. First is that I want to have a look at the stresses. They're still do not go or increase over a value of 30. Of course, I also have for if I go back to the control center, I also have for the shape optimization XY plots. I can show you here. No, this is topology optimization. Here I have, so again, I have a weight reduction. As you see here, we have the transformation of topology optimization to the new model. Comes with a slight increase of 10% of the weight, and this is again now reduced by the shape optimization, and now is even less than maybe, let's say, maybe about 10 grams less than the result of the topology optimization. And again, I look at the compliance, the stiffness of the structure. Okay, this is exactly at the 100%. So it reaches exactly the upper limit. And I have a look at the stresses with a slight violation here, slightly above the 30 MPa, but within the allowed tolerance. Here you see the absolute value. So this is little higher than the required 30%, but this is there we have a tolerance value, so we accept this as a solution. Okay, now we have a look at the shape we gained with this optimization, and here we see that's maybe the drawback of this shape optimization. What we gain with a 3D restraint in topology optimization with regards to overhang angle. This is a little bit destroyed. For example, in this area, I can show you very easy shown with a clip plane. I set into the model. You see, this is the way it should be printed, like this. This is the initial model. So you remember this was the result of the topology optimization. Here, a little violation of the overhang condition in this area. And now after shape optimization, it gets even worse. So this is what we don't want to have. So we do another variant of shape optimization. And now this is the same game as before in the topology optimization. I just go again into the free shape wizard and add additional condition again for 3D printing with a negative z-axis at print direction, and again a critical overhang angle, and now without any tolerance for the need of support structures. Save this condition and then save this variant of shape optimization definition as maybe as shape number 2. Okay, now I do a bit quicker. So now I can again edit my UCI file and just read the different file with a different optimization setting. But I don't show you in detail, just import the different results into. So this is 2 iterations more, as you maybe can see here. This is the coordinate change, and the other is the static. I also want the static results as also better the stress distribution. Okay, I load this. Maybe again, I also want to compare the XY plots of the 2 different runs. So this was the first run, and this was the second. For example, I can compare the final weight. So I see this is nearly exactly the same final weight. This is maybe, okay, it's exactly a little more than 1 gram difference in the final weight. And of course, I also want to know what's about the stresses. Again, we have slightly violated limit of 30%, but again within tolerance. So I'm happy with what I see at the XY plots. Now let's look at the final structure. Go then to the visualization dialog. Just look at the deformation. Now see, okay, now to avoid overhang, the need of support structures. This is maintained. I do again, just to have a comparison, a clip plane in this. There you can very good. Okay, now change the view of this. So this is the printing upwards, is printing direction. Now you see exactly this angle is maintained. There's no need for. Or it even gets better. This is a result after topology optimization. Still needs some support in this area. So this is shape optimization without a restraint on overhang angle. So it gets even worse. and now we have the shape optimization with a restraint on the critical overhang angle, and then we maintain the no need of support structure in this area. Okay, now if we're now very happy with this final design, maybe one can still say, okay, after shape optimization, the mesh does not anymore perfectly fit to the structure, so maybe we need a slightly more smooth version. So there's a simple opportunity. Just go back to the design wizard, choose the volume. Now that's simply all. And say, okay, we want remeshing, we want a finer discretization. For example, only half of the original element length. We want, of course, smooth the boundary. And then we need a fixed boundary nodes. Okay, we need to create, first we need to create the fixed boundary nodes. This is the same as before. I choose the areas of loadings and SPCs and the plane. So I choose this. And then also, no, first I did, sorry, I have an error. I go back to the visualization. First, what I have to do is to fix the deformation. So this means to fix the shape change done by optimization. Now this is, as to say, let's say frozen. So now I choose here these plane areas here. And also again the cylinder, and maybe here the surface. Create a set again. Name it again fixed nodes. Okay. Now we go back to the design wizard. Okay, we use all, and then we set half edge length. Now only very small smoothing, because we don't want to change the shape. We will just want to slight smoothing in this area, and we choose the fixed nodes, and then create a surface mesh again. Now we're nearly ready. Okay, now we have a very, very fine discretization. So in here you can again check how this new smooth surface mesh fits to the volume. So this is exactly the same structure, just a little bit better smoothed in this area. Okay, now we create a new component. We name this the final result. Create a new component, and now we have a surface mesh of the final result. Now everything what we need to do is now just to export this at an STL file. So we use this component, and we choose, maybe we name it finally STL, and here we are ready. Now this is the complete process from the FE model to the final STL file with a I want to say nearly printable design. I go back to my presentation just to do a short what's this summary. So as I said, what I showed you is a complete workflow from the design space. This means the definition of an FE mesh with some additional data, loads and boundary conditions, to a final design as an STL file you see on the right side. What is remarkable, that all simulations and all modelings are done within one tool. This is also something Mr. Schilder mentioned before. This is very important, because changing between different tools means always a little bit of losses of data and data getting more worse. So we are just within one tool and don't have the problem of data exchange. What you also see that we have a highly automated processes. This means that we have only little manual editing effort to go from a design space to a final design. And of course, what's important, especially in this area of additive manufacturing, that we have specific features for achieving nearly printable designs. And no, this is my summary. And now I'm at the end after, I think, 1 hour of lesson. So I thank you for your patience, and I'm ready to answer your questions. Thank you.